All right, I think we're live. Hello, students. That's a little bit after 8. Sorry for my tardiness here. This is Mr. Rich, and this is Mr. Rich Q&A on Sunday nights at 8 o'clock. So I'm here to answer your math questions. I've got a couple of questions that have come in for pre-calc. I'm going to knock those out. And then I don't have any others that I have received yet. So if you do have some questions about your math classes, go ahead and post them in the chat. That's our discussion forum here in YouTube. If you're watching on X, I don't think you can submit any comments, but you can do that over at my YouTube channel, Mr. Rich Math Coach. So feel free to do that. If you are one of my tutored students, you have my email that you can send me directly to my email address and tell me what questions that you have. You could post a snapshot of them and put them in there, and I'd be happy to work them for you. I do all math from Algebra 1 all the way through Calculus. So any questions you've got about any of your math classes, including ACT prep or SAT prep, I'd be happy to take those on. Well, I will pull up the first questions that I have. So give me a quick sec. I'm going to pull these out of my email here and slap them onto our whiteboard. So let's see if we can get this to work. And I don't think this is AP pre-calc, but that's okay. I think it may be like maybe a pre-calc honors that we are looking at here. And this is our first question. It says, write an equation of the line, moving this over here, that is parallel to the y-axis and passes through the point 4, 3. So this student has drawn a little sketch here, parallel to the y-axis, passing through 4, 3. So yeah, that would be a vertical line, right? At the x, passing through the x-axis at 4, and vertical lines always have that same equation, x equals whatever the x-intercept happens to be. So yeah, x equals 4 would be the equation of that line. Now, the slope, the question here that maybe the students right now, why not zero slope, point slope? So, you know, vertical lines are not really functions. And so they really don't follow point slope or slope intercept. They are kind of a unique thing amongst themselves. We're amongst all other lines. What we're really saying here is that when we say that x is equal to 4, what we're saying is that no matter what the y value is that you select, the x coordinate will always be 4. So if you say, what about when y is 2? Well, I would say x is always 4. How about when y is 100? Again, x would always be 4. So all of the points that you could possibly plot on this line, the y value, no matter what y value you pick, the x coordinate that would go with it would always be 4. That's going to make a vertical line. All right, the next question that came in from this student was one that I'm not too sure about, honestly. I'll show you the problem. I'm going to show you the root question here. This is a function, it's a function notation problem that gives us 3 functions, f, g, and h. And then the question, though, that she had was this one here. It was part F. And so I will pull this one in and try to slap that up there. It says to write the domain in interval notation for part D. And what part D was, I'll go ahead and just write this up here. Part D of this problem was saying G composition F of 0. Now, on part D, the student did find this is equal to G of F of 0. Right there. That's what G, this circle here means G composition F, which would be the same thing as this. So you are first to go find F of 0, which would be 7. And then it would become G of 7 because F of 0 is 7. Then you go here and you see that the answer is 9. So the answer to D is 9. So when they say write the domain for part D, I assume that what they are talking about is G composition f of x. I believe that that's what that means right there. But G composition f is just a quadratic because you would be, yeah, you would just be putting this quadratic into the G function, in which case it would be a quadratic function whose domain would be all real numbers, negative infinity to infinity. Now, the student here said negative infinity to negative 2 to infinity. I don't think we need to omit negative 2 from the domain. So I'm a little bit confused on that problem. If and I think this came in from Olivia. Olivia, if you had a question on this, or if you had a clarification on that, post it in the comments if you could, or you could even email it to me. Well, let's see what we've got coming up next here. All right, so if you are here, post a note, let me know where you are from, or if you're one of my students, feel free to post in the comments so I know that you're here. If you've got any questions, as I said, go ahead and put those into the comments. If you've got a math homework question, you could type it out. If you're one of my students, you can send me a photo of a homework problem, maybe from your AP classroom or from a homework sheet or something else, and I will definitely pull it up here and try to work on it. Well, what I do have, though, since I don't have any questions as of yet, checking my email, and I do have another question that came in. The question was, is there an easy way to memorize rules for trig derivatives? This is a question for Calc AB. An easy way to memorize rules for trig derivatives. Sure. I will mention a few things about trig derivatives. So I'm going to, let's see, put me back on full screen. I'm going to go ahead and pull something else up here. Let's see. And I will show you, what I'm going to show you is maybe a table of derivatives. So let's take a look here, going into my Calc AB archives. And yeah, this looks good. So I'm going to pull in a table of basic derivatives. And here we go. All right, let's go back to sharing my screen there. Thank you. And these are the rules of derivatives right here. Now, what am I showing you here? This is a table of basic derivatives. If you are taking a Calc AB, your teacher's probably not going to show you one of these. If you're taking calculus in your college class, this would be something they would show you. If you wanted to know, like, this would not be a comprehensive list of all the rules of derivatives, but this shows you how to take rules of a lot of the derivatives. And it also has a second part of integrals when you're going in reverse and you are doing antiderivatives. But for the first semester in your calc class, you're going to be learning most of these rules here. And what this student was asking me about are these trigonometric rules. So what I would say here, Anna, is that these are the three main ones here, right? Or let's talk about the two main ones that you need to know. The derivative of sine is cosine. And don't worry about the u prime here. This is that comes from the chain rule. But so the derivative of sine is cosine. Cosine is negative sine. The only thing I can tell you there is you just have to memorize those two, right? You know that they are derivatives of each other. Sine, derivative of sine, cosine is sine, but you have to know that the cosine derivative is the negative of sine. Now, why is that true? Well, the best way to understand that, hopefully your teacher is going to show you a graphical example as to why those two things are true. All right, I'm not going to go into it here. But then the next most important one to remember is that the derivative of tangent is secant squared. This can be easily derived with the quotient rule. I'm not going to do it here. I don't have a pattern for you. These are the three biggies here that you have to know. If you remember those, okay, if you remember those, the other three that are down here, kind of flow from those. And here's what I mean. Um, we we know that tangent is secant squared. So if you were to take the derivative of the reciprocal function cotangent, the secant will become cosecant. Okay. Again, I love a pattern for that. I just have to know that that's kind of similar but different is the way that I think of it, right? Secant becomes cosecant, but with a minus. Secant squared, negative cosecant squared. And then over here, secant is secant tangent. So, which is a little bit strange because the derivative of secant is itself times another function tangent. Again, these can be pretty easily derived, but I don't have a good answer for you, Anna, as far as like a pattern or an acronym or something to remember these by. You just have to use these enough to where you have them ingrained in your head. Okay. The most, I always tell my students, if you don't see a whole lot of questions on that require you to use these last three. You're going to be using probably those three, I would say 75% of the time when it comes to taking derivatives of tangent, of trig functions, those three here. Okay. And if I had to pick a fourth one, that would be like the most common one that you would be having to use. So these would be the four right here. Sine, cosine, tangent, and secant. Those come up, I would say, 80% are in those four. Okay, but thank you for that question. If you guys are already there in your Calc AB class, then you guys are flying. So that is for sure. All right, so I don't see any other questions that have come in. All right, looking over at Olivia here. Oh, interesting. So Olivia was saying that the boxed answer on that pre-calc question was from your teacher's answer key. Yeah, okay. So let's take a look. I'm going to look back there at Olivia's again. And let's see if we can find it. Yeah, this one here. Yeah, so for part D, for this one, G composition F. And eliminating, so they did say x plus 2 is equal to 0. Yeah, I don't see that because I think that would be if it was a rational function, if that g of x was in the denominator. So yeah, there's something that I'm missing, I think, on my end when I'm looking at the problem. Part D has to be something else. I'm going to go back and just take one more look. Oh, I can tell you what it is. Yeah, that's a misprint on the page because your teacher's answer would have been if write the domain and interval notation for part E. Yeah, because you can see there's a g of x down in the denominator. That's where you would have said, yeah, we have to exclude -2 from part E because you would then have an undefined function there. Yeah, that's what it is. So the domain, it would be for part E, it would be all real numbers except -2. So that's what that is. I think your teacher has a typo on part F that they were referring to the domain for part E, not for part D. Because part D didn't make any sense anyways because it was not a function of X. All right, I think we got that mystery solved. And then the janitor has one here. It says find C in the indicated interval so that the intermediate value theorem is satisfied. All right, so this is that is the function right there that he is referring to. Okay, so we are talking about 2x squared plus 3x minus 1. We're talking about the interval from 0 to 4 and f of c being equal to 1. Okay, that looks good. All right, so and let me show you what the question was. This was the question right here. Find c in the indicated interval so that the intermediate value theorem is satisfied. All right, so this is a Calc AB problem for sure. All right, so let me show you one thing here. Give me a quick sec. All right, so what we're going to do, here's what the intermediate value theorem says. And I'm going to just kind of write this out graphically to show you what the theorem is really referring to. So if you talk about the x value of 0 and 4, so here's our interval, 0 and 4. So what I'm going to do is I'm going to find the y value 0. Let's see where. Okay, so we need to find this c value. That was the question. But f of 0 right here, let's find f of 0. F of 0 is a -1. So we could plot this point down here at -1, 0, -1. And then we're going to find the value of our function at the other end of this interval 4, f of 4. So that's going to be 2 times 4 squared, 16, plus 3 times 4 minus 1. So this is 32 plus 12, 44 minus 1. Looks like that's going to be 43. So we would be up here at 4 comma 43. Now, if this function is continuous and it goes somewhere between those 2 points, then there has to be some value of x such that the y value is 1. Right here. So they want us to find this value of c, this value of x called c, such that the y value would be equal to 1. Now, if the intermediate, this is a continuous function right here. So all we're going to really do is set this function equal to 1. Like that, and we're going to solve it. And we're plugging c in for x. So I'll go ahead and put the c in for x. So we're solving 2c squared plus 3c minus 1 is equal to 1. Well, that is obviously a quadratic, so we're going to solve it by putting it into standard form. We'll put the 1 to the left side. So that'll give us this. And then we'll solve this by factoring. I'm going to solve this by just, if it can be factored, I assume that it can be. I'm going to do a trial and error method. So I know that I need to have a plus and a minus because the product of these two last terms has to be a negative, and I need them to add to be a 3. So I'm going to make this one a plus 2 and this one a -1. So that means the two solutions. So you can see that the outer product is 4c. The inner product is -1c, which combined to give me the plus c. So that's the proper factorization. So the two solutions, when you set those two equal to 0, is c is 1/2, c is -2. All right. So honestly, I'm not sure about the intermediate value theorem here. The question, I'm going to go back to that question again. I'm going to pull up his question. And here is the question. Find C so that the intermediate value theorem is satisfied. Yeah, so you can see that there's only one value here that is going to pertain to this theorem because it has to be a C value between 0 and 4, and that is going to have to be the 1/2. See, this value of x is -2. It's over here. Since this is a parabola, then what's happening is the function's coming back it's coming back up this way. When y is 1, there's another x value over here at -2. So the answer to this question is only the 1/2 value. Okay. All right. The janitor. I hope that helps you. All right. Let's don't see any other questions that are here. So what I'm going to do is I am going to go over some AP Pre-Calc. Now, most of the students that I work with in AP Pre-Calc are moving on to lesson 1.7, which deals with rational functions. So I'm going to do a little bit of work here. I think I'm going to maybe move this out just a bit, give us a little bit more room, since I don't think I'll be using Desmos. Although on a few of these, I think I will graph them to make a connection between the function and the graph of the function. So in 1.7, we are going to be starting looking back at rational functions. And most of what you're looking at in 1.7 is going to be kind of a redo of what you did in Algebra 2 in the second semester on rational functions. So rational functions are functions that have polynomials in both the top and the bottom of a fraction. And one of the characteristics of these functions can be that they have what's called a horizontal asymptote. And a horizontal asymptote is a horizontal line that the function will get infinitely close to, but not quite touch. It will not touch it. It'll get infinitely closer and closer the further the function gets out towards the right or towards the left. And for instance, if this dashed line was a horizontal asymptote, it means the function as it goes out to the right would get really close to it, but just not quite touch it. And it would do the same thing over on the left side. It could be either above the function and coming down to the asymptote, or alternatively, it may be coming this way. All right, so what we wanted you to get in Algebra 2, we wanted you to become really, really good at graphing all of the features of these functions. But one of the things we knew about horizontal asymptotes was that it really came down to by looking at the two highest degree terms in the numerator and denominator of your function. If you did have the degree on the top and bottom as the same, then that means you did have a horizontal asymptote at the ratio of the two coefficients. So in this case, I have x squared and x squared. So we definitely do have a horizontal asymptote, and that is going to be at the horizontal line y equals 3/2 right there, 3/2. Now, I am going to go ahead and graph this just so that you can see what this looks like. Hopefully last year your teacher showed you what these horizontal asymptotes look like when you graph them. You don't really see the asymptote. You just see that your function's getting close to where it would be, if that makes any sense. So if you graph the function, and then we put the function down in the bottom. All right, you can see it does some strange maneuvering here, has a couple of x-intercepts here, but you can see that it's flattening out as it goes out to the right and then as it goes back out to the left. What I'm going to do, though, is I'm going to go ahead and draw the horizontal line y equals 3/2 right there. Now, that line is not part of the function, but you can see that's the line that the function's getting closer and closer to the further out to the right and the further out to the left that you go. And you can see the difference on the left is the function's coming into that line on top of the line, and it does the opposite, coming in from the bottom underneath, getting close to that line y equals 3/2. All right, now let's go and do some more of these. This one right here, my highest degree term on the top is an x to the third, and the highest in the bottom is x squared. So this means that you do not have a horizontal asymptote. If the degree is bigger on the top than on the bottom, no horizontal asymptote. In a few lessons here in AP Pre-Calc, probably around maybe 1.9 or 1.10, we will see that this means that there is what's called a slant asymptote. It does have an asymptote, but it is going to be a line that is slanted, that has some sort of slope to it. And that would be the line that the function would get close to. And you will find that slant asymptote using polynomial division, which once again you learned in Algebra 2. So we will revisit that in just a few lessons. Well, let's go to number 3. What we have here is a higher degree term in the bottom than we do in the top. That means we do have a horizontal asymptote, but that's going to be at the x-axis, also known as the horizontal line y equals 0. So really simple to know if the functions are written in their standard form, whether there's an asymptote or not. Okay. Now, could it get a little trickier? Yeah, maybe. If they're written in factored form like this, you just have to stop and see what that leading term is going to be if you were to totally multiply out all of the factors. Here on the top, I would have a 10x squared as my highest term. Down here, I would have an x squared. So we do have a horizontal asymptote because I've got the same degree 2 on the top and bottom, and therefore the ratio of those two coefficients in front is a 10 over 1, y equals 10. Okay, so that is where that horizontal asymptote is going to be. All right. Well, this would mean that my highest degree term would be x to the 4th, because I would be multiplying x squared minus 3 times itself twice. X to the 4th over a 3x to the 3rd. There will be no horizontal asymptote. I've got a higher degree term on the top than I do on the bottom. All right, then what we're trying to get you ready for here is in AP Calc, we use limits to define horizontal asymptotes. So what we know about horizontal asymptotes, if you take a look, I think I'll go back here and I'll show you this function one more time. So this function here, which is this one, that does have the same degree top and bottom. What is happening here is that as x goes to infinity, the y values are getting closer and closer to 1.5, 3 over 2, to that value right there. So we can write that as a limit. And so we can come down here and say, since I can see that this has a degree of 3 and a degree of 3, that asymptote, that horizontal asymptote, will be the horizontal line y equals 2 over 6, or 1/3. That just simply means that the limit of my function as x goes out to infinity will be that value, 1/3. So the higher and higher x goes, moving out to the right on the graph, the closer and closer the y values are going to get to 1/3. And that would be the left one, right? So I'm going to change that to a negative infinity. This means going out to the left towards negative infinity, the y values approach 1/3. That's all that means. This is going to be the same limit. It's just that we're going out to infinity, to the right, but also getting close to 1/3. So honestly, there's not a whole lot new here. And let's do from a graphical standpoint. And let's do this one. It wants a limit statement. It says, write a limit statement describing the output values for the following graphs and verbal descriptions of the input values. This says the input values decrease without bound, meaning they go to the left without any boundary, meaning they're talking about what's happening as you go all the way out this way. Well, that would be a limit statement that says the limit as x goes to negative infinity of f of x is equal to this y coordinate of -1. They're showing us with this dashed line the horizontal asymptote at y equals -1. And so that statement is really that limit statement right there. This one says the input values increase. Inputs are the x's. So as the x's increase, meaning as you go to the right, what's happening? Well, that means you're traveling along this section of the graph right here. So as the input values increase, the outputs are getting infinitely close to the number 1. So we could say the limit as x goes to infinity of g of x is equal to the number 1. Well, that's lesson 1.7. I will work one other one here, but I will just make a few comments here. If you are watching live, right, some of you may be watching this, the recording after we've done this on Sunday night. But if you are here live, we still have about 20 minutes left, and you can submit a question to our comments here in YouTube. So feel free to do that. I don't see that any have come in. If you're one of my students that I tutor, you have my email address. And so you can send me an email directly to me of any homework questions that you want me to cover here in our live session. And if it's during the week and you have a homework problem that you'd like me to cover, just shoot me an email. I'll load it up here and have it ready to go on Sunday nights. You could watch it live. You could watch it on the recording the day or two after we run it on Sunday night. So however you want to do it, use this as an extra resource to get a homework problem answered. I will also remind you, if you are watching this live or on the recording, I wanted to remind you of a couple of things. If you are an AP Pre-Calc student, I do run an AP Pre-Calc group that is on Sunday nights. In fact, tonight, right after this, is our first live session. And in this group, what we're going to be doing is we're going to be doing a weekly live group session at 9 p.m. In our live classroom, closed just to the people in the group. And I'll take any questions and answers that you have. Most of the classes, at least in our area, they stay on the same pace. All right. So most of the classes are somewhere in the 1.6, 1.7, 1.8 lesson range. So we're always going to be in the same vicinity lesson wise. And you can send in specific homework questions. I'll try to cover as many as I can in our live session, just focused on AP Pre-Calc. In addition to getting access to that live stream with me, also we have a classroom that you get access to that has extra resources. So videos and extra practice problems, things that you could use as an extra resource to help you succeed in your AP Pre-Calc class. Because if you've talked to anybody who's has taken AP Pre-Calc or is in it now, or if you yourself are in it, you know that a lot of times those tests that your teachers give you, they feel a lot different than the homework problems that you were working on. If your teacher gives you work in Delta Math or in Flipped Math, you do the homework and you think, yeah, I think I know this stuff. And then you get into the test and you're like, I don't think I know this stuff, or this doesn't look familiar. The tests usually are at maybe a different level than some of the homework problems. And so you really have to do more work than just what your teacher assigns you. Okay, so that's why this group would be a really good thing for you if you want to get some extra feedback, get some a different viewpoint maybe from your teacher on some of the topics. I might be able to help you that incremental bit about to help you get do better on your exams. All right, so let's go back to the screen here. And before I leave 1.7, I think I will show you one of these slant asymptote problems. Now, we're not going to show you here in this lesson how to find the equation of the slant asymptote. That's going to be in a future lesson, but we do want to see what the limit would look like if you did have one of these slant asymptotes. So here on this question 15, you can see that the question is the input values increase. So the x's are increasing without bound. That means the limit statement is the limit is going of x is going to infinity. The function is h of x, and that means then that you're writing along this part of the function. As the inputs increase, you keep going higher and higher. That means those y values are going to positive infinity. All right. Over here on number 16, This statement says that the input values would decrease without bound. Well, that means the x's are decreasing, meaning they're going to the left. They're approaching negative infinity. That statement would be the limit of our function k of x as x is going to negative infinity. And following along here, what's happening as x goes out towards negative infinity, those y's are climbing and they are approaching infinity. That's what that looks like right there. That's lesson 1.7 in pre-calc. I'm going to do a little bit in 1.8. And again, this is a review from Algebra 2. Nothing new here. Let's take a look at these rational functions. These rational functions, at least this first one, is already written in its factored form. So you do have a second degree polynomial on the top, second degree on the bottom. One is a function 0, right? A function, when we say find the zeros, we're actually asking, what are the x values that will make the output or the y value a 0? Well, since rational functions are ratios or fractions of polynomials, the only time that this y value over here is going to be a 0 is when the numerator is 0. Fractions are equal to 0 when the numerator is 0 and the denominator is not 0. 0 over 6 is 0. So the question becomes, if you're going to find the zeros for a rational function, is you are going to set the numerator equal to 0 and solve it after you have removed any common factors between the top and bottom. So right here, I have zeros in this function at -3 and 2, because we would be taking each one of those factors and setting them equal to 0 and then solving. And we get that answer right there. Over here, I would set this numerator equal to 0. The 0 is 0. At x equals 0, I will get an output of 0. Pretty easy, huh? Now, over here, I don't want to call this one a 0. I don't want to say one of the zeros is 6, because those are going to cancel each other out. Therefore, I only have a 0 at x equals 3, and that is the only place it exists. There will be, as we'll see in a future lesson, this means there is a hole in the rational function at x equals 6. Well, let's take a look at number 6, and then we're going to move on and do some calculus for the calculus students. In this function, if we're going to find the zeros, we do need to factor the top and the bottom. The first thing that we'll factor here, hopefully you notice that there is a greatest common factor of x. So we're going to go ahead and pull that out, giving us x squared minus 4x minus 32. Now, I would want to factor this just to see if I do have any common factors between top and bottom. And I believe that can be factored, and I'm going to do it by trial and error. And I need two numbers that multiply to be -4, but add to be +7. I think that's going to turn out to be 4 and -1. How did I know that? Because I know that the middle term of quadratic comes about from the combination of the product of the outer and the inner terms right there. 8x, -1x. That's what produces the middle term 7x. So those are the factors of the bottom. But now what we need to do, and the only reason we needed to do that, because I need to know if I do have a factor up here that gets canceled by one of these down here, that will eliminate it from being a 0. But let's go ahead and rewrite this by factoring that quadratic, right? This is going to be x minus 8, x plus 4, right there. Right, I'm looking for, when I factor this when my coefficient is 1 right here, I'm looking for two numbers that multiply to be the -32 add to be the -4. That ends up being -8, 4. Well, it's a good thing that we factored the bottom because we do see that they have a common factor x plus 4. Therefore, that x plus 4 on the top does not produce a 0. It's going to be 2 zeros, x equals 0, and x equals 8. That would be my answer. All right, now I do want to show you what that function would look like if we did end up graphing it. And let's just confirm that that's what we get. And students, if you're in pre-calc, as you're trying to seek to understand problems and to check your work to make sure that it's correct and that you fully can make a connection between analytical work and graphical work, you do want to be doing this with Desmos. You don't want to do this on your T84. T84 is a burden when it comes to having to graph things. Things are really fast and simple and smooth and clean when you're working in Desmos and you have to graph. So here's our function. I think I've got that right. Double checking there. Yeah. So you can see as we zoom in here that there is an x-intercept right here at 8. So there's one of our zeros. There's the other 0. Now, we did get rid of this x plus 4. But let's go over and see that would have been a 0 at x equals -4. Let's go see what the graph's doing at -4 over here. So -4, let's zoom in a bit, is right here. Now watch what happens as I'm clicking and holding and dragging. As soon as I get over to where x is -4, you'll see that Desmos is going to display, if I can land on it, it's a little bit hard to land on it. I'll zoom in a bit more. That might make it easier. As soon as I get over here to -4, it'll turn into a hole right there. So I'm clicking and holding it right there. So when x is -4, the function itself is undefined. There's a hole in the graph. That's nothing new to you if you were paying attention in Algebra 2 last year in rational functions. That's the location of a hole. Desmos doesn't display it because it's really an infinitely small hole, right? Because the function exists at -3.99999. It exists at -4.000001, right? So it does exist there at those points really infinitely close to -4, just not exactly at -4, okay? So anyways, I just wanted to show you that, yeah, you can do your work here and then check it in Desmos and see if it makes sense. And you would be wondering, yeah, I know I crossed off x plus 4, but what's really going on at x equals -4? Those are the kinds of things that you have to do if you want to get an A or a B on your summatives in AP pre-calc. You can't just say, let me quickly do the homework. Oh yeah, I did the homework. Okay, did all the homeworks, ready for the test. It's probably not going to work out. The other thing, I probably mentioned this to you last week on AP pre-calc, your teacher should be assigning you work in AP Classroom, right? That's how you get ready for summatives. Those tests that you're doing are probably coming from AP Classroom. Your teacher's going to be pulling them from there. Or if they're using a joint test amongst the teachers, it's probably one that has come and been generated from a database that's in the AP Classroom that the teachers are using. So if you're not working the problems that are in there and you're doing things in Delta Math or Flipped Math or some other curriculum, probably not going to be good enough for you to get an A or a B on the test. I'm just telling you, that's the way that it is. All right, this is the third year of AP Pre-Calc, only the third year, right? So I've been working with students ever since we started this thing 2 years ago. This is the third go around, and things aren't really any easier or better. Great class, though. All right, so I am going to shift gears and talk a little bit about calculus. If you are an AP Pre-Calc student, you are going to find what I'm going to show you, I think, interesting. Maybe not, but try it and see, because I think it might make sense what I'm going to show you. What I want to do for the AP Calc students is show you where the limit definition of a derivative comes from. So I'm going to draw a sketch of a random function, a continuous function that I'm going to call f of x. And I'm going to start with something that really all algebra students from Algebra 2 through AP Pre-Calc would understand, and that's the concept of the average rate of change of a function. Even in the first semester, the first quarter of Algebra 2, we want you to understand average rate of change. Here's what average rate of change of a function is. If we pick 2 points on the x-axis, and we'll call them randomly A and B. So we're not going to assign numbers to them, but just call them generically A and B. That means that the y value would be f of A. It means you would plug that A value into the function for x, calculate an answer. We're going to call it f of A. And then this, of course, would be f of B. And especially those of you in pre-calc, you understand what the definition of average rate of change is. I'm going to call it AROC. And that average rate of change, we are trying to tell you, is f of B minus f of A all over B minus A. And that's even nothing new, because this even goes back to Algebra 1. Because in Algebra 1, what we said was that we called this x1 and this x2. We called this y value y2 and that y1, which meant that this was actually, what I just wrote here, was actually what we called the definition of slope. y2 minus y1 over x2 minus x1. That means then that if I drew a line between these 2 points, I'm talking about a straight line that passes through those 2 points. That line has a name. It's called a secant line. You've seen that name. The name's not all that important, but you've seen that name in your geometry class, right? It was a line that passed through a circle, through 2 points on a circle, called the secant line. So the average rate of change is the slope of the line that connects 2 points on a function. All right, now here's a problem that plagued mathematicians for centuries. That was how do we get not the average rate of change on a function? How do I get an instantaneous rate of change? That is, how do I get a slope exactly at 1 point, not between 2 points? Meaning, what if I wanted to get the slope of the tangent line right at this A value right here? Meaning that how could I find the slope of a line that would only hit the curve at that 1 point? The slope of that line would be the instantaneous rate of change of the function, not an average rate of change. Didn't have a way to do that until we invented differential calculus. So here is the thought experiment that leads to what we call a derivative of a function. In order for me to get the slope at this 1 point rather than between 2 points, I'm going to change my nomenclature here just a little bit. What I'm going to do is I'm going to call this point x. I'm going to call the distance between these 2 points h, which means that this x coordinate would be x plus h. And then I think you see what I would also have to be doing is changing the names of these y coordinates right there. All right, I didn't want to get rid of that. Okay, let's go back here. Where did I end up? There we go. I lost my place. There we go. I wanted to, yeah, okay, we got it. It's back. So I needed to rename now these two y coordinates. This would be f of x. And this one is going to be f of x plus h, like that. And then what I'm going to do is I'm going to write now the average rate of change with that nomenclature right there. So I'm going to go ahead and wipe this out. And you would agree with me that this would be f of x plus h minus f of x all over the difference between the two x values, right? Here's my rise, my the difference here, and the difference here would be x plus h minus x. And do you notice what would be in the denominator? Well, the x's would cancel. So this is just h right here. So here's the thought experiment. If we let this point slide ever so close, the closer and closer I move that point, the shorter and shorter h is going to be. And how far do I want to move this? I want to move it all the way on top of that point. The only problem with that is that this calculation would become 0 divided by 0, because there would no longer be a difference between the two y values, because the points would be on top of each other. And there would be no difference here. The h would have gone to 0. And I can't take 0 divided by 0. That number doesn't exist. So those of you that are in AP Calc, you've been working now this first 3 weeks on limits. So what we do is we say, okay, yeah, I really don't want that point to go right on top of the green point, but I want it to get infinitely close. So we take the limit as h goes to 0. If you take the limit of any function as h goes to 0 and you create that ratio, that right there is called the derivative of the function. We don't have time tonight for me to go over an example, although I think I will do one example. Okay, I have time. We have about 3 minutes. I have one example I'm going to show you. This right here, I always tell my students, right, this changed humanity right here. This gave us the ability in the sciences and in mathematics for us to find instantaneous rates of change of functions, which ended up being called differential calculus. And so this is what engineers and scientists use to get instantaneous rates of change of whatever the quantities are. I was an electrical engineer, so we were interested in instantaneous rates of change of voltages in circuits. How quickly is the voltage changing? How quickly is the current changing at any moment in time? And we use differential calculus. But let me show you a function very quickly, how that limit works. Now, this is where maybe this is going to not be of too much interest to Algebra 2 students for sure. But if I have a function x squared and I want to get its derivative function, that is the function that will give me the slopes, the instantaneous rates of change on the curve, I'm going to take the limit of that function using this ratio. So I'm going to say the limit as h goes to 0. Now, f of x plus h would mean x plus h squared, right? This means stick the x plus h in for the x. F of x is x squared, so I replace this f of x with x squared, and that's all over h. Those of you in AP Calc know that if I tried direct substitution right here, I would get 0 over 0. So what we have to do is we have to simplify the numerator. If you expand that square out, you're going to get this. And when you simplify that, what you see is the x squareds will cancel out right here. X squared and negative x squared add up to 0. Then you can simplify this ratio because we can factor out an h from those two terms, giving us 2x plus h over h. Those h's cancel. Now we can go ahead and substitute 0 in for h, and we get an answer of 2x. We just took a derivative. The derivative of this function is 2x. All right, so that is a derivative, and those of you in AP Calc, you should be learning that this week if you didn't start it last week. That's the limit definition of a derivative. All right, students, that's going to do it for tonight. Come back next week if you want to have your homework questions answered. Send them in to me if you're one of my students. If you're not, when you get here, stick it into the comments section. I'll be happy to work on it. Hope you all have a great week. I'll see you next Sunday night, 8 p.m. Bye.